Good morning, everyone. Today we are going to be talking about incremental analysis for benefit cost, and it's a way of comparing alternatives for projects that are public in nature. And so we've talked about the characteristics of public projects, and so we'll get into the details of that today. Let's look at a couple of announcements here. Your next homework assignment is due on Sunday, and also that same day you're going to, did you get this one? On that same day you're going to have an exam. And the second exam is going to be just very slightly different from the first one, in that there's going to be two parts on the exam. I'm going to have separate papers for the concept questions and for the problem-solving questions. We're going to have the exam in here, which gives you a hint that there will probably be a question related to Excel. I'm not going to make any promises. You can just expect whatever comes. And you can prepare a page of notes to remind yourself of procedures or whatever you'd like to have on the notes, but you can only use that for the second part of the exam. For the conceptual questions, I want it only to be based on what you remember and understand about the concepts, not about what you have written down on your equation sheet. So we'll just have that during our normal class time on Sunday the 15th. And yeah. I didn't say that. No. It'll be problem solving. Mm-hmm. When you remember, go ahead and ask. All right. Incremental analysis is what we're doing today. And you probably remember incremental analysis when we were doing the incremental internal rate of return. And it was kind of a logical procedure when we did that, and you were comparing alternatives by ordering them from the cheapest alternative to the most expensive alternative. And you were ordering them based on the initial cost, moving things to the present value. You can do incremental analysis, though, on the annual value or on the future value. But the way that we're going to order the alternatives in today's example is in terms of the cheapest construction cost to the most expensive construction cost. And then we look at the increment, meaning the difference between the two. We're going to look at the difference in the initial construction cost, calculate the difference between the maintenance and operation on an annual basis, taking that to the present, finding the difference in the benefits and the difference in the disbenefits, and then instead of each of these variables, C sub I, C, M, and O, and so on, we'll put the increments of those components into the formula. And today we're only going to be using the conventional benefit to cost ratio. We could do the same thing with modified, but just for simplicity's sake, we're going to use conventional. Now, maybe the tricky thing is knowing, once you've eliminated an alternative, what to do next. And so what we did previously was had several alternatives like A, B, C, D, and E. All right, so this is in order of least expensive on the left and most expensive on the right. So our first comparison, we said, was B versus A. And why did I write it like B versus A instead of A versus B? It's just kind of a pattern because B is the more expensive one. And so just to, in my mind, make me remember that I should do B minus A for all of the costs, benefits, disbenefits, that's why I write down the comparison in that manner. All right, so let's say that of the two, B is better. How will I know that B is better when I do the incremental analysis that we're doing today? When I do an incremental B to C analysis, what will be the criteria that tells me B is better than A? One more? All right, so if this coefficient is greater than 1, then what that means is the extra money we paid for option B is justified. It means there's more benefits for option B compared to option A. The incremental benefits are better than the incremental cost. So what that means, let's say option A was 5 million initial cost and option B was 6 million, the initial cost. If if the B to C ratio is greater than 1, the incremental B to C, that means the extra $1 million that you spent for the more expensive alternative gives you more than $1 million in benefits. So you're getting more benefits than you got cost. Okay, so let's say option B was the champion of this death match between A and B. So what's my next logical analysis? What do I have to compare next? All right, C versus B. So I do the B to C ratio, and let's say that in this case, it's less than 1. The incremental B to C is less than 1. So that tells me that B is better, C isn't better than B. What's my next analysis? Right, very good. D versus B. Since I've already rejected C, it's out. I don't compare the next thing to something that's been rejected. I compare the next alternative to our reigning champion, which is B. And so you always need to be thinking about what has been rejected and what was the second best option, or what's the best option so far. All right, everyone have a copy of today's in-class exercise? In this exercise, we're looking at dam construction. And it says in the problem statement that the dam is being constructed to prevent flooding, provide a source of water for fighting fires, and introduce recreational opportunities. And in the table that's provided, you can see that they've monetized each one of those benefits. They've calculated that the flood protection for option A, for example, is worth $520,000 every year. And the fire protection benefits is $52,000 per year. And whatever recreation they're going to do, maybe it's boating or fishing or tourism, I don't know. But whatever they've monetized for the recreational benefits is $78,000, and each of those is per year. There's also some disbenefits, though. Disbenefits, remember, are the disadvantages of constructing the project. In this instance, it's additional noise and congestion, traffic congestion for people living in the area around this dam. So from the pattern here, if I compare option A to option D, there must be something about plan D that minimized the disbenefits. Maybe that partly explains why it's more expensive. It's $9.5 million instead of $3.1 million. This project is going to last 75 years, and so some of these costs that are in the future you need to take to the present. So in part A, it says to find the present worth of all of these costs, the initial cost, which is already in the present, the maintenance and operation, the benefits and disbenefits. Then calculate the B to C ratio, and then in part C, start doing the incremental analysis. Ultimately, what we're trying to find out is which alternative is best. You know, should we spend $3 million? Should we spend $7 million? 9.5? We have to figure out what is getting us the biggest return. And the rule is keep spending money as long as you get more than $1 in benefits for each dollar of investment. Because if you can invest $1 and then get $1.50 in benefits, then that's a good investment. The second part, once you've completed the first spreadsheet, you should make a separate copy. You can copy a whole page onto the separate sheet and then start playing around with the interest rate. In question 2 at the bottom here it says, what's the highest interest rate that you could have and still find a project that has an acceptable B to C ratio? Okay, we have plenty of time to work on this today. In fact, it's only 8:11 right now, and we've got until 8:50. And the reason why I gave you so much time is I'd like you to try and figure out what the formatting of the spreadsheet should be on your own. You're getting to the point where you're experienced enough with Excel that you should be able to do the next step beyond just filling in equations and filling in numbers. You should start thinking of what is the format of the solution on your own. And that's a hard thing to do. You know, you're starting with a blank spreadsheet. I'll give you a hint. The first thing you should do is you should copy this table. But then after that, I'd like you to conceive of your solution pattern yourself. Give that 5 or 7 minutes, and if you're really at square one without any ideas, the pattern's on the back of my solution, at least. You know, every solution can look a little bit different, but I'd like you to try and figure it out on your own because we got plenty of time to do that. All right. So I'm going to stop talking and turn you loose on this problem. Remember, the first step, as it says in Part A, is find the present worth of everything that's an annual amount so far. I'll show you the solution that I put together. It feels good when you're working on your own spreadsheet and not someone else's, right? Okay. Let me remind you of a couple key points, and I think most people already figured this out, but to begin, you have to calculate the present worth of all of those amounts. And so rather than doing 75 rows to represent the 75 years, the initial cost was already in the present, so I just copied those over straight. But the maintenance and operation, just for example, I used the PV function and then I put the amount here in the payment field rather than making it a future value that had to be repeated 75 times. Yes. Unfortunately, it's not going to make these formulas up here any larger than they already are. Yeah. Okay, so here's the initial cost, maintenance and operation, benefits, and disbenefits. You'll notice that I combined all three of the benefits together into one column. And the way that I did that, here in the formula, in the payment field, I have the sum of this, that, and the final thing. So the sum of annual flood, annual fire, and annual recreation, all three together. So then here are the B to C ratios. If we were just comparing by the B to C ratios, which is what you shouldn't do, one of the points of today's example is to show that the one with the highest B to C ratio is not the best project, because we want to maximize benefit. We want to get as much benefit as we can that's economically justified. We don't want the biggest B to C ratio. We want to have, anytime you can spend $1 and get more than $1 back in return, then you should spend $1. You know, if at first someone's giving you $1.25 for every dollar that you spend, that's great. But even when they're giving you $1.10 in return for $1 of expenditures, you should still keep the exchange as long as you're getting more in return than you're giving. So that's what the incremental analysis is all about. So you'll notice that first was B versus A, where we find the incremental cost initial, the incremental cost maintenance and operation, and these are on a present basis, so we're finding the difference between the two, the difference in the benefits, the difference in the disbenefits, and so on. So B is definitely better than A, so let me put in a conclusions field. I'll call this which is best. And here I said B is best between the two. And then comparing C and B, it's clear that option B is still best, because if you get C, you're spending more in the costs than you get in the benefits. That's what the ratio less than 1 means. And then finally, if you compare D and B, D is best, because you're spending more money. You're spending $5.6 million extra initially, but you're getting more benefits and you're saving the disbenefits. There are fewer disbenefits, and so those sort of are combined with the benefits. If you look at the formula that we're substituting into, the conventional B to C formula, here it is. So we've used the delta B in the formula, the delta D, the delta CI, and the delta C maintenance and operation. So overall, in the Part C, through the incremental analysis, we concluded that option D is the best one that's available. The second question is, how high can we make the interest rate and still have a project that is justified? Now, it's these conventional B to C ratios that tell you whether a project is justified. It's not the incremental. And so what you're trying to do is keep changing this interest rate around until you find one where all you have is a 1 for the last option that stays above 1. So option B is the one that stays favorable the longest, and you can make the interest rate as high as 14.5%. if we make the interest rate lower? Yeah, so if you make it just 14, so 0.14, then the ratio is above 1. We want to see how high can you make the interest rate and still have the project be justified. So that means even if you had to borrow money at 14.5%, option B is still a justified project. None of the others are justified at that interest rate, but option B would. It would be justified. All right. So you have an exam coming up, and let me give you a suggestion on how to study. The homeworks that you've done and the in-class exercise, try going through them again without the template provided. See if you could figure out how to solve it using a blank Excel sheet as your starting point. Rather than just using a pre-existing solution, work through in your own, what are you actually trying to accomplish at the end? And that's a really great way to study. It'll really solidify the lessons in your mind. Let's go back to these announcements here before you finish for the day. Remember that homework 10, which I've just given you today, it's also uploaded on iLearn. That's due on Sunday. And then we're having the exam here in this lab on Sunday as well. And we'll also be back in the lab on Thursday. We're going to be doing more Excel things when we get together in 2 days on Thursday. All right, that's it for today. I hope you have a great day, and I'll see you on Thursday.